Hello. So today's class, I'm going to continue from page 153 of the workbook, where we used last time we had proved this fact that the circulation density of a vector, that's if we have like a little tiny square. What's going on with my vector field? Say green is my vector field. Vector field has some kind of flow. What's the circulation across that flow? And so let's find it for some vector fields. So for the first one, A, this vector field, Cx is called uniform compression. At 0, there's nothing going on. But as we go out from 0, there's larger and larger. Well, if C is positive, this is a picture for C is positive, it's expansion. If C is negative, we're going to flip the arrows. So what is the circulation for this vector field? So we would find dn over dx minus dm over dy. That's m and that's n. dn over dx is 0. dm over dy is 0 or minus 0. 0 minus 0 equals 0. So it makes sense if we take a little curve, a little circle. Any circle we make, it doesn't depend on where we go. There's no circulation across that circle. Cool. Now what about B? B is the uniform rotation. I think we graphed this one. Looks like this. And as we get further away, the rotation increases. So the circulation of this one, dm, dn over dx minus dm over dy, is C minus, check my work, negative C, so 2C. So any point we see in that space will rotate. The flow around that point is rotating. Okay, so let's do the last two for the homework. And you can see the interpretation of it. You know, if it's positive rotation, that means we're going clockwise. Oh yeah, this is counterclockwise. For C is greater than 0. And if C is less than 0, it's going to be clockwise. And this is called net rotation. Okay, so that's circulation density. Now let's go on to proving, we did circulation in the previous chapter. We also did flux, which is if we're got some kind of region, how much is our vector field going out of the region? Okay, so we're going to call x and delta x, delta y, our small square, and we're going to find the flux about this small square. Okay, so that's going to be same points as last time. And instead of looking at the circulation, we're going to look at adding up this vector, this vector, this vector, and this vector. So this vector has, along this distance, the vector field is fxy dx. And if we're going in this direction, how much is our vector field going in that direction? We'll dot it with negative j hat. And if we're looking at this vector field, how much is it going in the right-hand direction? We're going to dot it with I hat. That's 1, that's 2. This one, this vector, how much we're going in the positive direction here. Doesn't really matter whether we're going left or right because we're wanting to know which component is in that direction. So we're going to dot it with j hat, the upward direction. And this one we're going to dot with the negative x direction, negative I hat. So if we add these four together, I'm not going to go through all the work, but you get, add them up, combine, rearrange, you get something similar to last time. So if we want to know the flux density, that means we take this value and divide by delta x, delta y to get the flux density, also called the divergence of our vector field. So let's find the flux density of these same vector fields. So flux density is going to be dm over dx plus dn over dy. So for A, that was the expansion. This is going to be C plus C, 2C. And kind of makes sense. We see from this vector field, yes, there's expansion. Or at any point, it's expanding. So that's for C greater than 0, compression for C less than 0. To find B, we take dm over dx, which is 0, plus dn over dy, which is 0. So there's no expansion, compression. Which makes sense because it's rotating. So I'll have you do the next two for homework. All right. So these two facts, the flux density and the rotation density, circulation density, are used for Green's theorem. Green's theorem has two versions, and the way they use each one is interchangeable, as you'll see. What we need for this theorem is a curve that's simple, closed. That means it's made up of piecewise continuous curves. And we want it to be, and it's closed, meaning it starts and ends at the same point. And we want also something called positively oriented. This means we travel around curve, RV curve. The region we enclose is to the left. So you see if this is where I'm walking around the curve, to my left-hand side is the region. So this would be a positively oriented curve if we're going that way. If we're going the other way, notice the region that is closed would be to your right. Okay. So we're going to always consider that counterclockwise rotation. Okay, so Green's theorem takes a positively oriented, piecewise smooth, simple closed curve. So basically this curve here, and says if we know a vector field in that region, we can find the circulation. The circulation about F is going to be F dot T, this is the tangent vector, ds. And the way we can find that is, make sure I get this right from my notes, is across my curve M dx plus N dy from before. And now we know what this is. The circulation across our region is dN over dx minus dm over dy. Dx, dy, what we found for that circulation. And the same fact can be used to find, the same reasoning can be used to find the flux. Same assumptions, but now we're finding the flux, which is the force times the normal. N is the normal vector. Normal. So that's going to be M dy minus N dx Yeah. Which is dm over dx minus dn over dy. So we got the flux and the circulation. Green's theorem. So let's use it. Let's apply it. So here we have our line integral, something dy times something dx minus something dx. So if we call this m, we call this n, we see we have the flux version of Green's theorem. So if we're using a square, the unit square in the positive quadrant, we're going to have, this is our curve. So that's the circulation. It's not the circulation, this is the flux. If our vector field F is mn, so we just integrate around this region. Take the derivative m with respect to x, which is y, minus the derivative of n with respect to y, which is 0. So that's going to be y, xy from 0 to 1. For y, for x, this should say dy. That's y, dx, dy. Excuse me. So that's the circulation about that region. Or here's another example. If I have this integral, notice it's the form m dx plus n dy. Ooh, that's the circulation, m dx n dy. So we can find that by looking at, all right, like this. Tangent ds, which according to Green's theorem is whatever our region is, I take dn over dx minus dm over dy. That's a circulation version of Green's theorem. So now we got to interpret our region. We got the triangle with 0, 0, 1, 0, 0, 1. So that's our region. So we can say we're going from 0 to 1 on dx and 0 to 1 minus x on dy. That's the region. And so then we just find out what these guys are. dn over dx is going to be 2xy minus dm over dy is 0. 1. I find that. Did I do this right? dn over dx. Yes. So with respect to y, this is 2x y squared over 2. 0 to 1 minus x. It's not quite matching what I had in my notes. And but that's right. Okay, this is right. It just means more work for us. dx. So that's 0 to 1. Equals 1/2, 2/3 plus 1/4. That. Okay, let's make that common fraction. 6 minus 4 plus 3. 5/12. 6 minus 4 plus 3. Yeah, see if that's right. 5/12. And then let's do one more together and then I'll leave the examples for you guys. Okay. So outward flux is the formula dotted with the normal. So that's, if our region is the square bounded by -1, -1, that's going to be dm over dx plus dn over dy. That's the formula we got for the outward flux. So dm over dx is 3y e to the xy, and dn over dy is 2y. And this becomes 3e to the xy. Dot, dot, dot. 1. So I got 6e. Okay. So for homework, let's give you 1, 2, 3, 4. Check your parameterizations on these. And 5. That's all I'll give you. Very good. We'll see you on Monday. Bring questions. Thanks.